This presentation is about gallium nitride semiconductor technology for RF power applications. The work is led by Professor Dipankar Saha, and it was done at the Nanoelectronics Center at IIT Bombay.
Semiconductor technologies pervade modern civilization. They are ubiquitous in applications like computing and display to communications, sensing and actuation to power and energy conversion. However, most of the semiconductor devices in the world today are made of silicon. So where exactly does gallium nitride come in? Consider satellite communications. A satellite is required to transmit large amounts of RF power. That requires certain special kind of devices. Or consider a civilian application, 5G communications. Once again, you need to transmit large amounts of radio frequency power. Going beyond civilian applications, there's a huge plethora of military applications that require the same thing, transmission of RF power, such as in this application like radar and signal jamming. And these are technologies where India needs to be absolutely self-reliant. And these are where gallium nitride comes in because it's a robust semiconductor. It can handle large amounts of power at RF frequencies. As you can see here, this market projection shows how civilian and military applications are expected to grow very significantly over the next 6 years for gallium nitride RF devices. The story of GaN technology development in IIT Bombay starts with the fabrication of the first device in India back in 2010 by Professor Dipankar Saha's group. Since then, it has been a story of over a decade of continuous technology development with a focus on RF power applications. It's been a story of over a decade of steadfast support by the Ministry of Electronics and more recently the Department of Science and Technology. It has been a story of several years of collaboration with our space agency, which takes IIT Bombay devices, packages them, tests them, and gives us feedback on the performance. All of this has led to the maturing of the IIT Bombay capability to the extent that technology demonstration and knowledge transfer is now possible and underway with the defense company.
So firstly, we have designed the power amplifier using lumped components on our circuit design software. This power amplifier consists of a stability network, matching networks, and the biasing networks. We have then transformed this schematic into layout by replacing each lumped component with an element of the same value from our design library of passive elements, that is resistors, capacitors, and inductors, which are mainly realized using metal lines on GaN substrate. This is then followed by fabrication of these elements for the physical realization of the power amplifier.
Now, the process of making the gallium nitride power amplifier starts with designing the elements or the components. What you see here is a snapshot of the design process for the high electron mobility transistors, the key element. It's a process that happens on powerful computers by solving the equations of semiconductor physics. Once the device is designed, then you go into the fabrication lab and actually make it.
After the device design is ready, the actual fabrication of device begins. The fabrication of semiconductor device and monolithic microwave integrated circuit involves several sophisticated tools kept in a controlled environment called clean rooms. The complete MMIC fabrication is a 9-step patterning process and includes patterning by electron beams as well as UV light. Pattern making by electron beams is called electron beam lithography. This is an electron beam lithography tool. Pattern making by UV light is called photolithography. This is a photolithography tool. The MMIC fabrication process also includes several steps of etching, that is, removal of material from the unwanted part, metal deposition, dielectric deposition, and annealing. Etching is carried out in inductively coupled plasma reactive ion etching tool. Metal deposition is done in electron beam evaporator, and annealing is carried out in rapid thermal annealing tool. After going through all the process steps, The device is now ready to be characterized. This is an actual GaN-based substrate with HAMTs and MMICs. This small substrate of 2 cm by 1 cm consists of hundreds of HAMTs and several MMICs. This will now go to the characterization lab for characterization and analysis.
Now that you have seen how and where the devices are made, let me show you what they look like. What you are looking at here is the gallium nitride transistor, the active device responsible for power amplification. You must remember that these devices come courtesy very powerful microscopes. These tiny lines here that are responsible for the very high frequency operation are only 250 nanometers. That's hundreds of times thinner than a human hair. Now, the active device is not sufficient. You need a bunch of passive devices around it, and those are also fabricated in our lab. Once you have made the devices, they need to be connected to each other. For that, you need to make things like structures like these via holes through which you can have vertical metal lines. You have these air bridge interconnects which are standing on thin air. And you see here an example of an inductor, an element that uses such an air bridge interconnect. Now that the devices are made and we have looked at them under a microscope, it's time to take them in for electrical measurements into the characterization lab.
So this is the probe station where we characterize our devices after fabrication. So this is our PNA and this is our source meter, and this is the probe station where we actually keep the device and probe it. This is the chuck where we place our device for characterization. So to make the electrical contact to the device, we have these two probes. This is the microscope and this is connected to the screen here. So microscope is actually used so that we can monitor the movement of the probes as we are making contact to the device. As you can see here, this is our device and these are the two GFG probes that give the DC and the RF signal into this device. Okay, so this is our PNA and this is the source meter. So basically source meter sends our DC signal to this PNA, and this PNA generates the RF signal and it sends both of these signals from these two cables towards our device. And this PNA we control using that PC via MATLAB. So basically we send in a code that controls the output of the PNA.
This is the transfer characteristics of the device, this is output characteristics, and this graph shows the peak current gain cutoff frequency.
So in continuation to the measurement and characterization setup, so this is how the measurement data looks like. This is related to the TCIV simulation. So the rows represent the drain voltage and the columns represent gate voltage. Gate and drain are just two nodes of our HEMT device, which is a 3-terminal device. And all of these values inside a matrix represent the current values. And this is specifically the data that we need for the DC simulation. Now coming to the comparison between the measured and simulated points, as you can see for both the simulations, one of them, the first one is drain current versus drain voltage, and the another one is drain current versus gate voltage. So as you can see that the model that we have made completely simulate our hand device. Also, there is a complete overlap between these characterizations. Similarly, for the scattering parameters, this is how our results look like. Now, for advanced design system, which is a CAD tool for simulating these devices, we have made a symbolic representation. Inside the symbol of our HEMT device, there are two components. One of those components is for DC's IV simulation, and another component is for the S parameter simulation.
With experimentally calibrated models in place, the power amplifier design and fabrication finally come together, and you can see what it looks like right after this and what kind of housing it gets before it goes out into the world.
Hello, so far we have seen various fabrication tools and steps to make our GaN MMIC. The product we get from the process is this tiny die.
Having GaN transistor, capacitors, inductor, resistor, air bridge, and transmission lines.
all integrated on a single chip to make a power amplifier.
But hold on, our work haven't ended up yet. The process you have seen is only front end of fabrication. We can't take this to market in this form. We need to go for packaging, which include processes called back end of process.
Here this die goes for lapping where we thin down the substrate.
Then we drill microholes on this die from backside, the tool called deep reactive ion etching. Then we do around 10 micrometer thick gold electroplating on the back side of this die to connect ground points on the front side to the bottom ground plane. Now our die is ready to be mounted on the packaging, which include heatsink, spacer to make electrical connection from PCB to die. This is die, we mount it here, and from spacer lead to die pad we do gold wire bonding.
With that, our RF GaN journey for today is almost complete. We will conclude with a summary of the offerings from this group. The first is Fab Services, which entails the facilitation of indigenous GaN fabrication at a fraction of the usual licensing costs. The second refers to the supply of prototype devices and MMICs for GaN RF power applications. The third refers to design facilitation for RF power amplifiers utilizing either the IIT Bombay fabrication lab or third-party commercial fabs. The last point refers to the fact that all of the capabilities talked about can be easily customized for various civilian and strategic applications, notwithstanding our initial focus. That brings us to an end of this presentation. If you have any questions or would like to discuss, we look forward to hearing from you. Thank you very much.